Let's talk about polynomial functions. This is a broad category of functions that includes linear functions, quadratic functions, cubic functions, and so on. A polynomial function is made up of coefficients and powers of x. So in general, it's an x to the n, and then going on down with descending powers of x until we get to a constant term. Of course, some of those coefficients may be equal to 0. There may be some missing terms. So we typically write polynomial functions in descending order, from the term with the highest degree to the term with the lowest degree. And the degree of the entire function would be n, which is the highest power of the variable that you see. The leading coefficient of the function is the coefficient a sub n that goes along with this term with highest degree. So in this first example, I want to rearrange this function and write it in proper descending order. I would say here that f of x equals negative 2 x to the fifth plus x squared plus 3x minus 4. The degree of this polynomial is 5 because we have an x to the fifth as our largest power. And the leading coefficient is negative 2. That's the coefficient that accompanies the x to the fifth term. We want to note the degree and leading coefficient of polynomials because when we talk about sketching the graph of a polynomial, it turns out that the graph is shaped by the leading term. We say that the end behavior of the graph of a polynomial is determined solely by its leading term. Let's discuss that with a couple of examples. So say I want to begin to describe the graph of y equals negative x cubed plus 2x minus 5. The leading term here, negative x cubed, overwhelms the other terms as we look out to negative infinity and positive infinity. And so I can simply think about, well, what does the graph of the toolkit function x cubed look like? That is sketched below. Here's the graph of y equals x cubed. And we're performing a reflection on it to get the graph of y equals negative x cubed. The graph of y equals negative x cubed is going to be a vertical reflection across the x-axis. So the end behavior of the function above is the same as the end behavior of y equals negative x cubed. Those other terms, 2x and minus 5, don't really make a difference when we look out to positive and negative infinity. So when I sketch the graph of y equals negative x cubed plus 2x minus 5, I can say some things with confidence. I can say that in this quadrant, it's going upwards, and in this quadrant, it's going downwards. That's the end behavior of this graph. There may be some other squiggles in the graph, some turning points here in the middle because of these extra points, extra terms, 2x and minus 5, but the end behavior is the same as the graph of y equals negative x cubed. So let's describe this end behavior. We can use something called arrow notation to discuss end behavior. I can say that as the x values approach negative infinity, that means as we move to the left on this graph, the y values are approaching positive infinity. As we move to the left, the y values are going upward. And in a similar way, as the x values approach positive infinity, as we move to the right, the y values are going downward. So we say the y values approach negative infinity. This statement is a description of the end behavior of this polynomial function. Let's look at one more example. I want to describe the end behavior of the graph of y equals x to the fourth minus 2x squared plus 8. Let's just look at the leading term, x to the fourth. The toolkit function for y equals x to the fourth is shown here. It's similar to a quadratic function. It's just a steeper curve. So when I sketch the graph of y equals x to the fourth minus 2x squared plus 8, the end behavior will be the same as the toolkit function x to the fourth. So in this quadrant, the y values will be going upward, and in this quadrant, the y values will be going upward. Once again, there may be some unusual things happening in the middle here. Maybe it's crossing the x-axis a couple of times. There might be some turning points up and down, but the end behavior will be the same as x to the fourth. How do we describe this using our new notation? I would say as x goes to negative infinity, that means as we look to the left, the y values go to positive infinity. The y values are going up. And as we look to the right, as x goes to positive infinity, the y values are also going up. So y goes to positive infinity. Here's our statement about the end behavior of this polynomial.